Welcome back my dear friends, a very good morning, good afternoon and good evening to all of you, and this is the data analysis and decision making 1 course under the NPTEL MOOC, and as you know this is a 12-week course of total number of hours being 30. So, there would be 60 lectures, considering that each week we have 5 lectures and each lecture being for half an hour, and I am Raghunandan Sengupta from the IME department, IIT Kanpur. So, if you remember, we were discussing about hypothesis testing. So, in hypothesis testing you have some statement made by one entity and you want to either verify that or refute that. So, when you want to basically verify that and refute that, what you want to take is basically take a set of observations from the sample as a sample from the same population, and then based on your inference, your deduction, you basically conclude that the statement being made by the other person is right or wrong. Now, inherently, as I mentioned, that you will always consider that the statement being made by the other person is false. Hence, you will basically try to have H naught framed in such a way that you will always try to deny that fact, considering that H A, which is basically the alternate hypothesis, you are trying that to be true. Now, in the other cases, you should also remember that when you have some population parameter, basically something to do with the population parameter in which you want to basically disprove or prove, and it can be other statement also. Now, in the hypothesis testing, if you remember the table which we discussed in the 19th class, so the class just before, this is the 20th one, as you can understand, there were 2 type of errors. So, considering H naught to be true, actually being framed by nature or being given, you prove that that is true. So, obviously, there is no error. Another case would be H A is true and you prove that H A is true. So, there is no error. So, the error only comes on 2 occasions, that means H naught to be true and you prove that H A is true, that means you disprove H naught, case 1. Case 2 being H A is true from the other side and you give H naught to be true, that means you disprove H A, in that case there is the other error. So, these errors, if you remember, are considered as an alpha and beta, and this alpha is intrinsically related to the level of confidence which was 1 minus alpha. Now, if you go to the other example where I discussed about the bank, and you being the manager of the bank, you are trying to give a loan, the loan actual points which you will assign to people, and based on the points, if it is more than 70 or 60, you will give a loan, and for people less than 60 or 70, you will deny the loan. But there would be sets of people who should be given the loan, but you deny the loan, that is opportunity cost lost, and there are other set of people who should not be given the loan, but you give the loan, those are bad debts. So, if you remember, I have drawn that the 2 distributions, normal distributions with a certain mean values for both of them. The mean value for the people whom technically are not able to pay the loan are on the lower side, people who are technically able to pay the loan are on the right hand side, and the straight line, which was basically the overall score based on which you will give a person a loan and not give a person a loan, that was in between. Now, trying to basically reduce alpha would increase beta or vice versa. So, I also mentioned that trying to basically reduce both at the same time is not possible. What you try to do is try to basically minimize the sum of them. But in technical terms, when you solve the problem, we will keep beta fixed at a certain level, and then basically given the H naught to be true at a certain level of significance, which is 1 minus alpha, we will try to basically solve the problem. Now, I also mentioned that in this hypothesis testing and basically the concept of interval estimations are basically follow up on the concept of point estimation. So, if I will ask for forgiveness, but I am going back to the concept. If you remember, for point estimation you use the maximum likelihood estimation method and the general methods of moments. I just discussed them conceptually, I did not solve any problem, and I only gave the results. So, once the point estimation problems have been found out, and then you basically check using the concept of unbiasedness and consistency, then you basically formulate the interval estimation problem depending on what is the interval, and you basically find out the lower control limit and the upper control limit. and based on that you proceed. So, this lower control limit and upper control limit would be framed in such a way that they will depend on 1 minus alpha, which is the overall area covered in that PDF between the lower control and the upper control. Also, I mentioned that this values of upper control and lower control would differ depending on whether you want to find out something to do with the population mean or something to do with the population variance. If it is something to do with the population mean, there are two cases. Case 1, when you know the variance of the population, then you actually use the Z distribution. Obviously, there is no degrees of freedom for the Z distribution. When you want to find out something with related to the population mean, but the variance of the population is unknown, then you will use the T distribution. T distribution will be utilized considering there is a degrees of freedom and you will lose 1 degrees of freedom, because you are trying to replace the population mean by the best estimate with the sample mean. So, when you utilize the standard error or the best estimate from the sample, which is the best so called replacement for the population parameter, which is the standard deviation of the variance, you divide by 1 minus 1 divided by n minus 1, and in place of mu you replace it with x bar n. Why it is 1 divided by n minus 1? Because you lose 1 degrees of freedom, but as you are trying to utilize the set of observations which is x 1 to x n for the first time to find out something to do with the population mean using the best estimate, which is the sample mean. So, obviously, in the first case when you are using the Z distribution, the left control and the upper control and the right control, that means the lower control and the upper control limit would be a function of the mean value of the sample as well as Z values whatever you take, and Z values would obviously depend on the 1 minus alpha value, which is alpha value. Then when we go to the finding out something to do with the population mean given the standard deviation of the population not known, again you will find out the lower control limit and the upper control limit based on the fact that you have the sample mean, the T distribution with n minus 1 degrees of freedom, and also Sn. Sn means where you divide by n minus 1. I am sorry I am repeating it time and again, but it will become clear to you as you solve the problem. Then once we came to the concept of the interval estimation, we utilize the concept for the population variance. You found out there were two cases. Case 1, when the population mean was known, in that case you use the chi-square with n degrees of freedom, that means you are not losing any degrees of freedom. And in the second case, when the population mean is not known, you utilize the chi-square with n minus 1 degrees of freedom. In the first case, when you are using chi-square with n degrees of freedom, you will be using S dash. In the second case, when you are using chi-square with n minus 1 degrees of freedom, you will be using S without the dash. So, now in the third case when we come, you want to compare the differences of the two population mean. So, obviously, in that case when you are trying to find out, I am talking about the interval estimation case. When you are trying to basically find out the difference of the population mean, then obviously you will use the sample mean difference, but in that case you will first check up if both the population variances are unknown. If the population variance is unknown, you will basically use the Z distribution. If the population standard deviation of the population variance are unknown, you will use the T distribution, but in this case remember that in the T distribution you will lose 1 degrees of freedom from the first population and 1 degrees of freedom from the second population. Now, when you come to basically the case of trying to find out the ratios of the standard deviation of the population or ratios of the variances of the population, then you will use basically the F distribution. In the F distribution, the degrees of freedom are technically m comma n, provided the population mean in both the cases are known, that is mu 1 and mu 2 are known. In case if mu 1 and mu 2 are not known, then you will basically use the F distribution, but with the degrees of freedom being m minus 1 and n minus 1, and basically solve the problem. Now, when you try to utilize all these concepts which I talked in the case of hypothesis testing, remember the rules remain the same, but there are 3 cases for each of the problems or the instances which I mentioned. Case 1, say for example, you want to basically find out something to do with the hypothesis testing based on the fact the H naught, under H naught, I will not repeat H naught in each and every case. So, I will basically mention it for the first time now, and then basically only repeat the H A for each and every different instances. Considering the H naught is the case where under H naught the mean value is equal to mu naught, and there are 3 instances for this problem. Case 1, when HA is such where a mu A is less than mu naught. Case 2 is in the case when mu naught is greater than mu A is greater than mu naught, and the third instance being when the case when mu A is not equal to mu naught. For all these cases, technically the interval estimation problem was basically provided the population variance was known, you basically use the Z distribution and solve the problem. So, in this case you will have one set of problem, the hypothesis testing, where the values you will reject H naught if and only if the values of the actual set of whatever the sample information is given lies on the left hand side of the lower control limit. In the case when mu A is greater than mu naught, you will basically reject H naught if the values of the set of information which you get from the sample lies on the right hand side of the upper control limit, and in the case when it is mu A is not equal to mu naught, you will basically have that it is depending on where the values of the sample informations are given, that mod of that difference between x bar n minus mu naught would basically be greater than less than equal to the actual sample statistics which you have found out. Similarly, when you go to the case of trying to find out something to do with some hypothesis testing, something to do with the concept of the population mean, provided the variance is not from the population is not known, you will use again the 3 instances. In one case less than the lower control limit, next case greater than the upper control limit, another case in between. So, but in this case remember that in place of Z distribution you will be using the T distribution with n minus 1 degrees of freedom. And obviously, remember another thing which I completely forgot to mention, that when you are trying to do the hypothesis testing of the less than type, greater than type, the Z value provided sigma square is known would have a Z value would have a suffix of alpha. But in the case when it is not equal to, in that case Z values on the left hand side and the left hand side would be Z alpha by 2, because you will be taking the overall area in between the upper control and the lower control limit as equal to 1 minus alpha, which is the level of confidence. Now, similarly, when you come to the case of finding out the something to do with the population mean value, provided the variance is not known, you will use the T distribution as I already have said few minutes back. But in this case the T distribution obviously n minus 1 degrees of freedom remains true, which is there is no problem in that. But in that case for the less than type you will use alpha, that means the suffix in T n minus 1 would be alpha. In the other case when it is greater than type, again it will be alpha the suffix, and in the case when it is not equal to, the suffix would not be alpha, but it will be alpha by 2, because the overall area between the lower control limit and the upper control limit, that is the lower value and the upper higher value should be 1 minus alpha. So, we will be utilizing, so we discussed till this and we will be utilizing that time and again for the different types of parameter of the population you want to find out with depending on what set of informations is given. So, whatever I missed is basically the recap in details about what you have been doing in the last 2 class, which is the 18th and the 19th one, and basically I will continue more in details discussing in the 20th class also. Now, consider that the statistical inference problem is the hypothesis testing for the variance only, and here we consider the H naught is mu is equal to sigma is equal to sigma naught under H naught, versus the case where H A, which is the alternative hypothesis, is such that sigma is equal to sigma A and sigma is of less than sigma naught. So, in this case mu is known. So, if in this case if the mu is known, first I will draw the diagram. I will keep drawing the diagram for each and every rule such that it becomes clearer to you. So, basically you have the chi square, this is the value which you will have with n 1 minus alpha So, in this case it will be chi square n is the degrees of freedom because you are not losing any degrees of freedom, because if you remember this is when I am not going to highlight, but I am hovering my electronic pen. So, you see this S star, that means you have not, you are using the mean value of the population itself. So, there is no loss in the degrees of freedom. So, and this would be 1 minus alpha based on the fact the area onto the right hand side basically would be given by 1 minus alpha. So, S dash square by n should be less than of sigma square naught under H naught into chi square n to 1 minus alpha by n. N is the degrees of freedom or the sample size. So, if this is true, then you will basically reject H naught. Now, coming to the case where you have greater than type. So, I first draw the diagram and just mention that. So, in this case, remember again the rule is S dash square is greater than sigma square naught into chi square n alpha by n, but now note down important thing, it is alpha and 1, not 1 minus alpha. This is the nomenclature. So, alpha being the fact that the area still to be covered onto the right is alpha. In the case when you had the z distribution, the z values were symmetric, that is why they could be written down as minus z alpha and plus z alpha. Similarly, for the t distribution, as sample size increases, it becomes symmetric, hence also this nomenclature of using in the suffix 1 minus alpha or 1 minus alpha by 2 with respect to the case of alpha or 1 minus or alpha by 2 does not happen, because that is not relevant, but in this case it becomes relevant for the chi square and the f distribution. So, in this case you will basically reject H naught if S dash square is greater, that means on the right hand side. Now, when we come and obviously the hypothesis is H naught under H naught mu is equal to mu naught with sigma is equal to sigma naught with respect to the case that H A being sigma is equal to sigma A, where sigma A is greater than of sigma naught and mu is known, the mean value of the population is known. Now, the final case for this, under this is the statistical inference problem for the hypothesis testing for the variance. Under H naught sigma is equal to sigma naught and under H A sigma is equal to sigma A, but in this case sigma A is not equal to sigma naught and the mean value of the population is known. So, let us basically draw the distribution. If so, you have two values. So, this would be chi square. I will first write down the chi square. So, obviously, you are not losing any degrees of freedom because the population mean value is known. So, you can safely use n, you can safely use n. Now, comes the interesting part for the nomenclature. So, this area and this area should be alpha by 2. This area should be 1 minus alpha. Now, what you will try to do is that the area for the under the nomenclature scheme, the suffix would be 1 minus alpha by 2, that is the overall area which is still to be covered on the right, and this will be alpha by 2 corresponding to the fact that the area still to be covered on the right is alpha by 2. So, if you note down it, this becomes clear. So, in this case you will reject H naught if S dash square, obviously dash is true because mu is known, is less than on the left hand side sigma square chi square n and 1 minus alpha by 2, which is basically what we have basically written. So, it is corroborates the fact that the nomenclature and the way we are trying to basically give the rules actually absolutely match. So, there is no confusion. So, this becomes 1 minus alpha by 2 as it is, and in another case it will be if it is greater than type, because you are taking the fact it is not equal to. For the greater than type, S dash square is greater than sigma square naught chi square n, and this is alpha by 2 as rightly noted down, is alpha by 2 divided by n. So, obviously, both the rule as well as the nomenclature are matching, and there is absolutely no error, no confusion here. Now, let us come to the fact that we are trying to find out something to do with the variance, but the population mean is not known. So, if the population mean is not known, the next question would be coming that obviously we will be using the chi-square, but in that case the degrees of freedom would be reduced by 1, because you are utilizing the sample set of observations x 1 to x n for the first time to find out something to do with the population mean by the best estimate, which is the sample mean. Point 1. Point number 2, in the case if we are using the sample mean, obviously in that case S dash is not used, it is S, because we have lost 1 degrees of freedom. So, S is the formula where you divide by n minus 1, and in place of mu you use x bar n. So, let me draw the distribution chi-square. The left part is chi-square, this area is alpha, this area is 1 minus alpha, this will be chi-square n minus 1 and 1 minus alpha, because on the right hand side. So, I highlight it. So, if it is less than type, so obviously it will reject. So, let us see this chi-square n minus 1 1 minus alpha is exactly here. So, that means you will reject h naught if s square by n, n is basically mean the sample size is less than sigma square naught under h naught chi-square n minus 1 1 minus alpha and divided by n minus 1, because you have lost 1 degrees of freedom. So, this is the hypothesis testing for the case when under h naught sigma is equal to sigma naught, under h a sigma is equal to sigma is equal to sigma a, but sigma is less than sigma naught and mu is unknown. So, of the greater than type, what it happens, the hypothesis testing is under is h naught, sigma is equal to sigma naught, under h a sigma is equal to sigma a, and but sigma is greater than sigma naught and mu obviously is unknown. Chi square, so obviously it will be n minus 1 and this will be alpha and this will be 1 minus alpha. I will use the highlighter. So, if you consider this, let us see the nomenclature which we are using and the rule, they match. Obviously, we should come to the rule and match with our nomenclature. So, also vice versa whatever it is, but let us see its matches. So, you will see the rule is it is to reject h naught if s square n is of greater than type onto the right hand side of sigma square suffix naught, chi square n minus 1 which is right, alpha because the area onto the right hand side is alpha, that is the nomenclature is matching, divided by n minus 1 which is the due to the fact that you have lost 1 degrees of freedom. Finally, for the case so, I will first write the degrees of freedom. So, this is alpha by 2. So, this becomes alpha by 2. This would be 1 minus alpha by 2 because this is alpha by 2. This is 1 minus alpha. So, this is we are drawn, let us see. So, and the hypothesis is h naught mu is equal to mu naught, no, sigma is equal to sigma naught versus h a, where sigma is equal to sigma a is not equal to sigma naught and mu is unknown. So, in this case it is on the left hand side or the right hand side. Okay, let me highlight it as I have been doing, sorry for that. So, if you are following the same type of drawing, we should follow it. So, in this case rule is rejected if that means reject h naught if s square is less than type on the left hand side or on the right hand side. So, the first case is less than type, this is sigma square naught chi square n minus 1 obviously, and this is 1 minus alpha by 2 which is matches, divided by n minus 1 because you have lost 1 degrees of freedom, and or the other case is true where s square is greater than sigma. So, that means on the right hand side of sigma square naught chi square n minus 1 by alpha by 2, which is also matching with the nomenclature and as the rule says divided by n minus 1. Now, we will just mention, I would not give the rule, but I will try to solve it later on with the problems. So, difference, if you want to find out the difference between mu 1 and mu 2 provided sigma 1 and sigma 2 are known. So, what do you do? So, first pause, let us think. So, if sigma 1 and sigma 2 something has to be found out, obviously the distribution has to do with something to do with z and t, they cannot be anything else, point 1. Point number 2, let us find out what are the sets of information as given. It is given as sigma 1 and sigma 2 unknown. So, if it is known, so obviously you can rule out t distribution. So, it is z. So, in this case you will use a z distribution. If it is less than type, it will be minus z alpha. It is greater than type, it will be plus z alpha, not by 2, because mod by 2 would not be coming, and if it is not equal to, then only minus z alpha by 2 and plus z alpha by 2, point 1. Point number 2, the best estimates for the difference of mu 1 and mu 2 would be x bar n 1 minus x bar n 2, where n 1 and n 2 are the sample size which you are taking from the first population, and n 2 is basically the sample size we are taking from the second population. Hence, x bar n 1 and x bar n 2 are the best estimate of mu 1 and mu 2. Now, obviously, you will basically have a pooled variance. I will come to that formula. Pooled variance means basically what will be the variance of both of population 1 and population 2, where the standard deviation or the variance for population 1 and population 2 are given as sigma 1 or sigma 2 1 square and sigma 2 or sigma 2 square. Now, when it is not equal to, obviously, I mentioned that, I am again repeating it, then in that case it will be z alpha by 2 on the left hand side and z alpha by 2 on the right hand side. When it is the difference of mu 1 and mu 2 provided sigma 1 and sigma 2 are known, but equal, in that case be rest assured that if they are unknown and if they are equal, then immediately the word unknown should strike. In that case z distribution will be ruled out, you will use the t distribution. Now, in the t distribution, when there was only one population, you lost 1 degrees of freedom, but in this case as you have two populations, you will lose 2 degrees of freedom. So, t would be with the suffix n 1 plus n 2 minus 2, where n 1 and n 2 are the sample size from population 1 and population 2, that is point 1. Point number 2, when you are trying to find out the difference of mu 1 and mu 2, obviously the best estimate from the sample would be x bar n 1 and x bar n 2. So, where x bar n 1 and x bar n 2 are based on the fact that n 1 and n 2 are the set of samples which you are taking from population 1 and population 2. And obviously, the pool variance would now be replaced by the corresponding standard errors from population 1 and population 2, that means from the sample 1 and sample 2, and you will calculate accordingly. Here also, in the case when you have left hand side, that means less than type, it will be I am just talking about the mean points. It will be t suffix n 1 plus n 2 minus 2, and it will be given by alpha because of the less than type. For the greater than type, again it will be t suffix n 1 plus n 2 minus 2 alpha, and in the case when it is not equal to, it will be given by t on the left hand side t n 1 plus n 2 comma minus 2 obviously comma alpha by 2, and similarly for the right hand side it will be t n 1 plus n 2 minus 2, and then in that case also it will be alpha by 2. But alpha by 2 and for the z1 and the t distribution would be as they are symmetric, hence the concept as we have used for the chi-square and the f distribution would not be used. That means 1 minus alpha by 2 and alpha by 2, those things would not be utilized. Then again when we have the difference of the mu 1 and mu 2 provided sigma 1 and sigma 2 unknown, but unequal, the whole concept remains the same as second bullet point, only the sampled pooled variance or the standard error for the pooled sample, the formula would change, and we will utilize the same concept for all our calculation. With this one this lecture, I will end the 20th lecture and continue more discussion about the chi-square distributions problems and the f distribution problems, and then slowly go into the multiple regression. So, these parts would be more applicable as you solve the problem, as I basically discuss very simple problems, and if you basically solve it yourself. Both the assignments, obviously assignments are from the grading point of view for this NPTEL MOOC course, but if you basically read the book and try to solve them, things would be much clearer for you. And thank you very much for your attention, and have a nice day. Thank you. Bye.